Hello everyone, my name is Cullen, and I'm part of the technical team here at Inorix. Today we're starting a 6-part series on enterprise file supply chain transformation. In this series, we'll explore how the role of file transfer is changing inside modern enterprises, and why many organizations are beginning to rethink how files move across their systems. This first session focuses on the strategic background behind that shift, and the paradigm change we're now seeing across industries. Over the course of this series, we'll look at the challenges organizations face today, the limitations of traditional transfer methods, and the architectural principles that are shaping the next generation of enterprise file movement. Let's begin by looking at how the role of files inside organizations has evolved. For many years, businesses viewed files as simple outputs, like reports, logs, or backups. These files were static assets, primarily stored and accessed later when needed from storage systems. Digital transformation has redefined the role of files. Modern businesses continuously generate operational data like inspection images, transaction logs, and AI datasets. These are active components driving business processes, not just passive storage objects. The value of files now hinges on their quick movement between systems. Delays in transfer can delay data analysis and business decisions, reducing competitiveness. This makes file transfer core infrastructure in the file supply chain. A traditional supply chain includes production, transit, storage, and consumption. This structure applies to files, where production maps to devices and servers, transit to networks, storage to systems, and consumption to analytics and service systems. While physical supply chains are carefully designed, file movement is often a simple copy operation. A poorly designed file supply chain leads to missing files, delays, duplicates, version mismatches, and security incidents, impacting operational reliability. The historical human-centric model involved manual file movement via FTP, upload, and download. This worked when file volumes were small, transfers were occasional, and networks were simple, relying on manual verification and retransmission. Modern environments are fundamentally different. Millions of files are generated daily across complex networks, leading to frequent interruptions. The human-centric model cannot scale, making automatic, system-level file transfers essential. Now let's move on to Chapter 2, the explosion of complexity, focusing on networks and infrastructure. Corporate networks operate with multiple isolated segments, including internal networks, DMZ zones, OT networks, and cloud VPCs. These networks are not directly routable, creating challenges for system file exchange. The traditional solution is VPNs, but this introduces complexity that scales exponentially. Managing VPNs for many branch offices quickly becomes unmanageable, as network growth outpaces linear scaling. In smart factories, OT and IT networks are intentionally separated for security. However, files generated in OT systems still need to move to IT systems for analysis and management, posing operational challenges. When direct connection is impossible, companies resort to inefficient methods like physical USB transfers, intermediate servers, or manual uploads. These workarounds increase security risks, operational inefficiencies, and management complexity. Modern enterprises use multi-cloud environments like AWS, Azure, and Google Cloud, each with different regions and authentication structures. Files must move across these distinct environments. Traditional, single-server-centric transfer systems fail in multi-cloud environments. This results in inefficient cloud-to-cloud transfers and increased operational complexity. Modern infrastructure requires scalable architecture for direct file movement across distributed environments. We are moving into Chapter 3, which focuses on the illusion of speed. We will explore why measuring instantaneous bandwidth is not an accurate measure of overall file transfer performance. Many companies believe they are fast because they measure only instantaneous transfer speed, like 800 megabits per second. However, this single number doesn't represent the entire transfer process. Real transfer performance includes preparation time, connection time, transfer time, retransfer time, and integrity verification. True performance is measured by the total completion time of the entire job. Consider a 10 gigabytes file transfer that fails at 98% completion. Traditional methods require restarting and sending the entire file again, resulting in a retransfer cost of 100% of the file size. Hidden delays like firewall configuration, port opening, and server installation all contribute to preparation time before a transfer even begins. Long preparation time significantly slows the overall process. Now we transition to Chapter 4, the zero-copy security philosophy. which addresses how files are handled structurally during transfer. The traditional structure is source to hub to target. This architecture creates an intermediate copy, increasing the number of points for access control, backup, deletion management, and audit responsibility. Intermediate storage increases the operational burden by requiring management of access permissions, backup policies, retention control, and expanding the audit scope. More storage points mean more management complexity. The zero-copy architecture changes the flow from source to hub to target, to a direct source-to-target transfer. This means no intermediate storage is used. Zero-copy security principles require that files exist only once during transfer. Data transmission is encrypted, integrity is verified automatically, and policies are controlled centrally. Security is built into the architecture. We move on to Chapter 5, Extreme Reliability, which focuses on designing for failure rather than assuming perfect network stability. In real network environments, failures like network outages, device reboots, power failures, and packet loss occur regularly. Stability means the job still completes, even when these failures happen. Enterprise networks frequently experience temporary disconnects, device restarts during transfers, and unstable WAN connections. Systems must be designed specifically with these common failure scenarios in mind. True enterprise resume capability detects the exact interruption point, verifies previously sent data, identifies damaged chunks, retransmits only those damaged sections, and restores the file to a complete state. Without advanced resume, large files must restart from the beginning, dramatically increasing retransfer costs and making completion time unpredictable. Reliable systems must support automatic recovery. In conclusion, for Part 1, the file supply chain is a design target, and file transfer is a strategic agenda. Automation is critical. To achieve full digital transformation, companies must intentionally design their file flows,